Food radiation probably one of the classical technology that has been proven safe by so many different scientists and so many different government agencies around the globe. Yet, this is one of the technologies which is not commercially viable, or like it's not commercially practiced because of the lot of misunderstanding from consumers. So, the food radiation is relatively very simple. You take the product, you package it, and then you subject to certain ionization radiation, and the radiation source can be X-rays, gamma rays, electron beams, and it kind of has a certain energy dose called kilograys, and then you are going to treat that for a certain time, then you are done and your product is safe. It can be quite effective, inactivate virus, bacteria, parasites. It can do insects. It can do delay in maturation of fruits and vegetables. But one of the common concern is radiation kind of came in the 1900s and then subsequently evaluated in the 1950s and 60s. At about the same time, we had World War I and World War II, where the atomic bombs were developed and destroyed and so on. So people were skeptical about radioactivity, and when you say I'm using radiation, they also worried that radiation will make the food product radioactive. So they worried they don't want to consume the product because they think, okay, that's going to make me sick, all those things. And they also worried that radiation make people with more cancer, birth defect, and so on. The other thing people worried that companies can take a spoiled product, radiate it, and then make it better. Again, that's not true. You cannot take a spoiled product, use any technology to make it a good product. That's never going to happen. But that's a rumor people probably trying to spread because they worried about radiation. In 1905, the patent was issued for radiation. 1940s, MIT has done research with ground beef, and then one of the major milestones that changed the radiation life is 1958 Food Additive Amendment. The US Congress at the time decided that when you process food with radiation, you have to label that, and they consider this as an additive. So what that means is when you are high pressure processing, you don't need to say in the labeling statement it's high pressure processed. When you are UV treating or you are using pasteurization, you don't need to say it's a UV pasteurized or thermally pasteurized. You have that product. Whereas when you pasteurize or sterilize with radiation, you have to use a symbol called IDORA symbol, which we'll show later, and that's called food additive amendments. And as a result, whenever people see that radioactive, the IDORA symbol, their mind automatically goes to radioactivity, and then they say, okay, I don't want this product. So it kind of became a major challenge. But otherwise, if you look at in 1970, astronauts goes into moon, they took radiated products with them, and then 1980s, WHO said, radioactive, radiation is safe. So it's kind of repeated after repeated. Many different governments said it's safe, but the persistency of consumers, particularly in the US, has kind of become strong. In India, I think it's relatively acceptable, but many other countries it's not. Another interesting thing, at least from the US perspective, is whenever there's a major outbreak, consumer probably more receptive to accepting radiation, and with passage of time they forget that, and then they are against radiation. So, some of you probably too young to remember this, but probably in the 90s, there's probably thing called Jack in the Box. There's a major meat outbreak in the one coastal area of US, and a lot of children died, a lot of people eating meat died. Then there's a major outcry why we don't invest in radiation so that we radiate beef so that it's safe. Then when the time passed, people become resistant. Then there are recently, for example, there are outbreaks with consumption of produce. Then people said, why we are not radiating produce with radiation with some of the leafy greens and so on. So that kind of ups and downs goes with the time, and but nevertheless, consumers always go back. It's negative, so that's a kind of an issue basing radiation. The other thing probably related to the radiation, people think the treatment facilities like where they have gamma rays and so on, they think it's like a nuclear reactor, and they think that if there's a meltdown of that gamma columns, it becomes, the neighborhood becomes radioactive, all those things, even though those type of fission type of things never happens with the radiation type applications. So there's a lot of misinformation, but over the years, whenever there's a major outbreak, the researchers always come back and show the benefits of radiation, whether it's a meat or fresh produce and various other applications. So this is one of the true non-thermal technology. You can package it, and you can even do this with the frozen conditions. There's no chemical preservative, so that means today we call this as a clean label, but this is demonstrated in the 50s and 60s without even knowing it's kind of the term. And it has a low energy. Today there's a lot of talk about sustainability, reducing energy use, and this is one of those things. And then you also have relatively lower operating cost. You probably have high operating costs. So this is a major issue, consumer acceptance. And then people worry about the resistance in microorganisms, maybe radioactive more resistance. So there's a discussion about toxins. Many of the non-thermal technologies may not be good in inactivating toxins, and same thing with radiation as well. So that's some of the potential disadvantages. So the radiation is called so much energy. It's 1 kilogray means 1 kilojoules of energy per kilogram of treated product. So we kind of saw the term pasteurization and sterilization. Same thing can be adapted for here. What they mean reduration, they apply 1 to 5 kilogray. This reduces spoilage microorganisms, so increase the shelf life. Radiation means a little bit higher dose. It may be more like pasteurization. Radioapatization means greater than 10 kilogray for commercial sterilization. So a lot of times they limit this high dose maybe around 30, 40 kilogray, so that you kind of have more controlled radiation treatment for sterilization applications. Low dose means you can able to control the insect grains, sprouting, you can ripening, prevent delay the ripening, reduce the problem with parasites and so on. So it's kind of very mild but effective in number of different ways. Medium dose, it's more pasteurization, like you can do inactivate various vegetative bacteria, and then you delay the mold growth and other fruits. High dose is more commercial sterilization, and you can able to sterilize the food, and then you can able to make that safe. So radiation can be delivered by 3 different means: gamma ray, X-ray, and E-beam. These are all same dose of radiation, but gamma rays comes from more natural source. E-beam and X-ray, these are human made, so that means it's made. So when it's a natural, that means you could constantly deliver that radiation dose. Whereas E-beam and X-ray, like the Tyndall X-ray, you go to the doctor, you can turn it on when you want it and you can turn it off when you don't need it. So, gamma rays is more commonly used, and it's basically coming from cobalt 60 cesium 137, and usually this is kind of come in the shape of a rod, and then you tip the rod inside a big water pool, and when you want to use it, you raise the rod up, and then you kind of bring the product, just pass around the rod so that it receives the radiation treatment. I have a better picture in the next slide or two. And the one of the things is, since it's always on, you have to shield it. So, that means you have to place inside a 7-meter depth of water, or you can put inside a concrete column. So, in other words, this radiation is only for the food, but if you operator for some reason get into that, you will see later on some slide, we are very susceptible to radiation. We will get sick or die eventually if you expose the radiation. So, that is where you have to kind of do it, but we are not going to die by consuming radiated product, because radiated products never become radioactive. So, gamma rays here, like I think you have some source of gamma rays, and then you are going to expose the product, and then it kind of gets this treated. Now, if you look at there, I mentioned concrete or aluminum lead for preventing radiation coming there, because lead or concrete is quite effective in stopping the radiation. So, when it comes to a lead door, it is not going to pass through. If it is a concrete door, it is not going to pass through. Otherwise, paper, metals like aluminum, it can penetrate. So, it is kind of quite effective in that sense. Now, ionization radiation, remember, this is a form of energy. So, that means it is similar to microwave, infrared radiation. Like yesterday we saw some of the ionization, like I think electromagnetic spectrum. This is the gamma rays in the one end of the spectrum, and so that means its end of the spectrum, this has a high energy source. So, that is why it is quite effective in terms of killing the bacteria, but without destroying the nutrients. So, if you have a radiation plant, gamma radiation plant, you technically it is in one location, and you may have prepared your product, ship them to your facility, and they may be loading them, and then let us say that they are going to send this into a conveyor belt, and then the conveyor belt is going to go through this treatment chamber. In the treatment chamber, you are going to have several of these radiation room with this radiation gamma tools. So, the conveyor belt is going to go around that, so that the conveyor is moving a particular speed. So, you can control how much time the product is sending near that treatment zone, and you also turn them both left and right, different sides, so that you can see that the product is exposed all around, so that you receive the proper treatment. After treatment, the products come here, and then you can do unload, and then you can distribute, and so on. So, when the treatment chamber is not in use, these bars, they are going to be lowered inside this storage pool. Like remember, I said a big water pool, you can put it inside, so that they do not affect the humans or others when the system is not in operation. E-beam, it is a human made, it is a lower energy compared to the gamma rays. It has a longer wavelength, it has a lower penetration, it also has on up capability. You can use a linear accelerator to produce, and you have a maximum energy about 10 millielectrovolt. It is not radioactive, but it does not have as much penetration as gamma rays. but you can able to shorter exposure time. So, again you have a linear accelerator, you treat the product, or you have a beef and then you can pass it through a conveyor belt and then you kind of expose. So, you adjust the speed of the conveyor belt so that you can able to adjust the treatment time. So, like I think these type of things are good for ground patties. Again, you can process quite a bit, and then the cost is about 2 cents per pound in the implant system. X-rays, these are similar to the tendon X-rays. You may go visit the doctor, and here your electron beam is accelerated and collide with a metal target like tantalum or tungsten, and it produces the electron, and that is where you are going to have the X-rays generated, and again you expose the product for certain time and you can able to get the treatment done. One of the things, remember, in all these technologies we always emphasize on the uniformity of the treatment. So, in this case the ionization radiation is a uniformity. Let us suppose you have a big beef patties here. So, when you do the treatment, you are going to apply only in the top, it may only go so much depth, the bottom portion may not treat it well. So, you may have to make sure that you treat both up as well as down, so that it is kind of treat much more uniformly. So, that the maximum dose probably in the top is received, but maybe in the center it receives somewhat kind of less treatment, but you kind of look at that treatment, make sure that that is sufficient to kill your target bacteria. The same way, the packaging has to be properly selected, so that the package allows the passage of radiation, and then it also do not create a radiolytic compound. So, when radiation pass through packages, some packages chemicals react with radiation and produce what they call radiolytic compounds that may be harmful to human health. So, you have to what they call pre-qualification of packaging material. So, in other words, you are a person interested in radiation of some beef patty or vegetable, you have to select a approval list of packages, so that they are free from some of those effects. So, if you have don't properly select that, then you are going to have incomplete penetration, but because the package does not allow that, and then this is to uneven dosage, then you are going to have potential problem. Now, there are something called dosimeters are used to measure radiation. So, remember we talked about conveyor belt, where the product is going through the radiation room and then comes out. So, oftentimes they along that product they put a small miniature disc, like for today's, if you want to compare, these are like you have this small Apple tracking devices, where you can kind of know where the location of your package and so on. It is kind of similar to small chip like thing, you can put inside the product, but they have certain chemical compounds like alanine, amino acids or dyes and so on and so forth, that change their property with the exposed radiation. So, with that they can able to measure whether or not that batch of samples receive proper dose of radiation, because we do not have a thermocouple, we do not have a pressure transducer to measure the ionization radiation, whereas the dosimeter can help to measure that. The other thing is, oftentimes people do not when the radiation room is active, operators do not go inside that radiation room, but nevertheless after finishing that they may have to go back and inspect all those things. Then they have to carry the dosimeter just in case there is a radioactive leak, is there any accidentally they exposed, that the dosimeter can help to identify some of those potential risks. Now, the microbial kinetic parameters, we talked about d value, the same d value concept can be applied here. So, usually it kind of lists as a D10, and then you have d values measured in the room temperature or freezing conditions, and then atmospheric conditions and so on. So, if you look at here, the d values for viruses 10 to 200, bacteria 10 to 50, insect 0 to 0.01 to 1, and higher animals you can see 0.005 to 0.1. The higher animals include humans. So, that means we are highly susceptible to radiation. So, that is where you have to make sure that you properly protect yourself as an operator before getting into the radiation room. Whereas, if you look at here, bacteria has a 0.1, 0.5 to 10, whereas viruses you probably 10 to 200. So, they are more resistant than the bacteria. Why? We will kind of explain that in a minute. And then the other thing is, if you look at the fresh versus frozen product, you can see that E. coli has 0.24 to 27, 0.31 to 0.4, Listeria 0.27 to 1, 0.5 to 1.3. So, the idea here is the fresh has relatively less resistant, the frozen is a little bit more resistant. The reason is when you freeze, the available water is kind of frozen. So, that means they are not readily available for the microbes. So, that means when you send the radiation, that radiation signal or dose is not transmitted to the microbes. So, they tend to have higher resistance, but nevertheless you can able to inactivate them with a little bit larger dose. The type of food, that means the complex food have a more resistance than the simpler food. Moisture content, again with the lower water activity, you are going to have less effective, like many of the treatments, probably like whether it is a thermal process, high pressure process, PEF, many of the technologies, they are not effective with the low moisture content food. And here the dosage levels for different leafy greens and microorganisms are given, and then again you can see that you are going to have different different products, different microorganisms have different sensitivity. Again, this is the data for different meat products with the different microorganisms. So, generally like many other processes, when you treat at room temperature it is effective, but when you add some more heat it is even more effective, and because the microorganism repair mechanisms are impaired by high temperatures. Same way when you freeze it, it immobilizes the water and prevents the diffusion of free radicals to the microorganism. So, they tend to have a little bit more resistant compared to room temperature. Other thing, if you do not have air, anaerobic conditions, it is also less lethal effect with the radiation, and when you have more oxygen content you can have more lethal effect. And you also similar to high pressure PEF, some of these microorganisms can be sublethally injured. So, that means when you allow the right conditions and nutritious medium, it allows the growth and recovery of the microorganism. So, you have to pay accordingly. Generally, the gram negative organisms, gram positive organisms are kind of easily inactivated, whereas spores and viruses have most resistant because of that chemical and structural property, and then how they recover from the injury. One of the things is lot of the vegetative bacteria, they are going to have DNA, and radiation can affect the cellular function. They break the cellular strand or double strands, so that they do not function. When you look at viruses, they probably do not have that, they are very tiny particle. So, that is why they tend to be more resistant compared to vegetative bacteria. This slide, just to illustrate the same point we talked in the earlier slide, you have to compare the dose requirement for keeping the product safe against the dose needed for keeping the product proper quality, and then there is a balance between these two. And if you make error in one side, you are going to have a food safety problem. If you make error in the other side, you are over processing. So, for example, you have observed dose and certain effect on the quality. So, this is the minimum dose where you may be killing all the vegetative bacteria, E. coli and things like that. And then this is a dose where you are going to have all these quality issues, lipid oxidation, color change, off flavor and so on. And you can see that there is a small window here where you can kill the bacteria effectively, but you do not have quality issues. Whereas, if you go this side, lot of high dose, you are going to have quality problem, whereas if you come in the other side here, you are going to have a food safety problem. So, you kind of want to avoid this and try to have a proper window where you can have both food safety and quality. Because I think today, in the interest of maintaining food quality, sometimes people just overlook the food safety, but you have to kind of try to make sure that food safe, because people do not mind if the quality is a little bad, sometimes they are okay, but nobody want to eat a product and die even if it is a premium quality. So, you kind of want to pay attention to that. Packaging, pre-qualification is needed, because sometime if you do not have certain packaging compounds, you are going to have irradiated compounds formed, and that may result in migration of compounds, which is not good. So, you kind of want to avoid some of those there, so that you have packaged with the proper shelf life. So, in 1966, FDA required labeling of radiated products, and so since 86 they started using the RIDA symbol, and so that means you have to show this symbol here, which shows treated with the radiation. So, now if you the only exempt is ingredients. So, that means if you are processing a big batch of vegetables, fruits, or you have a meat product which is consumed normally part of the meal, you have to use the radiation symbol, and then when people see that, they may kind of get a little bit negative perception. On the other hand, the ingredients are exempt. One of the commercially available ingredient today, most of the places, which is radiation treated. Anybody know what it is? A product which is treated radiation wise, but it is commercially available, spices, because normally spices could be treated with ethylene oxide or some other chemicals, but people do not want the chemicals. So, that is where it is radiated, but since nobody is using say half a pound of spice part of their meal, is only add a small quantity, you do not need to declare that part of the labeling statement. So, that is where consumers consuming spices, but not necessarily worried about radiation effects. So, because of that Congress thing, radiation is classified as a additive, and that is why it is part of the statement. And with the packaging, FDA required pre-market approval, and that can be very lengthy process. Now, different countries probably reviewed radiation and kind of mentioned it is safe, including FAO, Food and Health FAO, Food and Agriculture Organization, Codex, things like that, but usually they are all very positive. On the other hand, the consumer acceptance kind of vary. So, for example, Brazilian consumers are more positive, whereas European consumers tend to be a little more negative, US consumers are negative towards radiation. So I think the consumer education is a key trying to improve the consumer acceptance of radiation product. And part of the reason today is lot of the with urbanization and globalization, lot of the consumers removed from the farm, they do not know how the products are grown in the farm and things of that nature. So, for example, an average urban kid may not know where the milk is coming from. To them it may be coming from the grocery store rather than from the farm cow and so on and so forth. So, this is where the consumer education, how different process technologies help to preserve the product, help to preserve the quality and nutrition probably is important. And in that sense, radiation is a very wonderful technology, scientifically very sound one, but it is underutilized because of the lack of consumer acceptance under the current circumstances. I kind of mentioned earlier, people kind of spread a lot of misinformation. Radiation use may lead to the meltdown in a gamma radiation facility. The facility can explode because it has a lot of fissionable material, or they worry that it maybe has food become radioactive, or it creates a lot of radiolytic chemical compounds, and they allow the treated spoiled food with radiation and make it fresh. But if you look at some of these things, even thermoprocessing, the same thing can be said. You can take a spoiled food and treat it and then make it safe, but nobody worry about thermoprocessing because people feel comfortable, whereas radiation, something the unknown technology, they fear about it, and that is where a lot of the misinformation may be coming from. So, in summary, radiation show a lot of promises in maintaining safety, sensitive properties and shelf life, but it is very poorly understood. It kind of create a lot of confusion and misunderstanding. As a result, it is an underutilized technology. So, one of the key challenges, try to overcome that and then try to do better education with the consumer education. And how do you do that, and how do you educate the consumer and then maximize the benefit of radiation is probably a challenge for both food scientists as well as the food processors. And here are some selected readings, and I will be happy to have some discussion.
Hello sir. So, my questions are too basic and can be the consumer oriented. So, isn't it authorities making a consciousness or bringing a consciousness in the mind of consumer by putting the Rudda symbol? If it is acceptable or in the acceptable limit, it is safe. So, why to put the Rudda symbol on those products? Because we are not labeling, we are trying to hide the labeling as over processing or processing parameter. So, isn't it there the it is the intervention of authorities which is making the people to have a consciousness that it is unsafe?
Right. The concept of Idora simple specifically applicable the products made and sold in the United States, where the US regulations require any irradiated product to have that symbol there, because its irradiation is considered as a food additive. So, it is an act of Congress. Only the Congress needs to redo that legislation so that they remove that requirement. But with the legislation process, there are so many priorities. This is one of the lesser priority. It did not get the traction, so that they did not have that done.
So, second question is, sir, we are listening about the term radiation processing. Sir, just as we pronounce or we put these words into the picture, then it creates a bad impression on consumer. I have seen, just like on the first day also, we have taken the example that even the director of such a premier institute in India is also taking that word, has a bad impression in the back of the mind, in the subconscious mind. So, being the food engineering background people, where we are losing control that we are not able to justify us.
Right. Like again, there are people talked about using different terms for radiation. Instead of using radiation, cold, uh, cool radiation or something. I probably don't remember at the moment, but I think still in the broader literature the term radiation is there, so it's kind of what used. But maybe perhaps a different branding of the technology name may help, but that probably takes time and effort and communicate that benefits to the consumers.
Yes, sir. Sir, since we are talking the technologies such as pasteurization, sir, you told the example, it is sir 70s, 80s times of times technology. But sir, where we are lacking, my main concern is where we are lacking, or the industries are lacking, or the authorities are lacking, that we are not able to synchronize us to deliver the benefits to the consumer. Where we are lacking, it is the academic problem or industries or whole as an integrated problem of a society, or it is a consumer unacceptability of the processed food.
Right. As far as radiation is concerned, the discussion I had is primarily limited to US, but I think it may be similar here or different in India. And again, it's probably country to country, different countries have different regulations. But in overall, this particular problem came from the more what I call rule making process rather than scientific one. And then that presence of that symbol constantly reinforce the consumers something about this, because they don't see that symbol for thermally pasteurized products or even high pressure pasteurized products, because these are all considered physical processes, whereas in radiation it's there, so that's why it's reinforces. So I think you understand that, but I think it's probably something. There are organizations trying to address this, but so far this has been a limitation.
Sir, we are talking about the high pressure processing. Sir, in process we are dealing with the immense pressure. Sir, so are we in the status, social status, that we can employ that unit in the industries, because industries are located nearby the cities only. So if it collapse or a pressure leak is there, sir, it could be more than hazardous what we can think, because it can collapse around, I think I was hearing about analogy that it can collapse the building of entire agriculture department of IIT Kharagpur if it pressure leak is there. So sir, we are in social status in USA or in India that we can employ that.
Sure. So that's again part of the misinformation. So high pressure processing, the technology equipment kind of originally developed and devised from material science or those type of engineering disciplines, and the pressure vessels are designed and fabricated as per what they call American Society of Mechanical Engineering ASME code. Okay. So with that, what they also have, they probably have some built-in safety mechanism so that the pressure vessels doesn't explode and disintegrate. Number one, they have this wire wound concept, so it can expand, contract, rather than just bust into small pieces. So I think that's number one. Second, many of them probably have a built-in what they call safety disc. So what that means is, let's say for some reason the pump decide to keep pumping more and more fluid. Let's say you set 600 megapascal, pump want to build in say 1000 megapascal. The safety disc is probably have a safety mechanism, it busts to open say 600 megapascal, 650 megapascal, so that the pressure buildup going to stop and it's not going to happen. So most of the high pressure vessels using the commercial equipment today, they are built with wire wound technology, and all of them have this safety mechanisms part of the built-in process. So you're never going to happen some of those issues.
Sir, could you please repeat the first one?
Okay.
I'm not able to.
Okay, so So, what is the second reason I said? Like okay, so first one is probably the wire wound technology. So, you can have a pressure vessel monoblock. So, that means you can just take a piece of steel and have a pressure chamber, and then with the repeater use, that pressure chamber can create a crack, and that's where you can say crack open that can burst into pieces. But that type of vessels not used in the industrial scale. They are using wire wound technology. So, that means they take pre-stressed steel and then they kind of form a wire like chamber that can expand, contract within the pressure levels, so that they can be much more flexible and nimble.
Thank you, sir.